Next, Josh and David Chandler are going to present their Snow Hydrology 101 module. As they're presenting, I'm going to ask, I think it would be interesting to think about how you could use some of these modules in your classes, which I see coming up in the chat, but also in this era of COVID and high flex teaching, which is a lovely new invented term, how might you help colleagues by recommending some of these modules to them? So we think, how could you use these, but also how might, who might you recommend them to?
Great. All right. So yeah, we put together some slides to talk about our module. So I'm Josh Roundy. I'm at the University of Kansas, and we also have Dave Chandler, who's at Syracuse University. So this is our module. So the module outline really is to help students develop a fundamental understanding of snow hydrology, learn the terminology, learn the basic processes, and then apply that through sort of a capstone project where they're going to look at snow energy balances using a model and looking at the relationship of seasonal snowmelt, timing, and volume relative to climate and sort of climate forcings. So that's sort of the main idea. We've broken it up into 5 different sections. So the first section looks at just the basics of snow, talks about the processes, and then it talks a little more about snow and meteorology, and then talking about how we do snow measurements, and then talking more about snow modeling, and then final capstone activity where they kind of bring everything together to do a report kind of based on a sort of consulting aspect of a perspective of consulting. So I am planning to use this module in my water resources classes that I'm teaching this fall. So it's a senior level design course where they've had hydrology, they've had some exposure to snow hydrology in that class, but mostly was pretty basic. So really looking to utilize that, and in that sense, I know Dave is looking to use this more for course that he teaches specific to snow is just one part of his snow course. So, all right, so throughout the whole module, we kind of focus on 2 sites for a lot of our analysis. So these are the 2 sites that we're looking at. We have so one in Idaho, so Reynolds Creek, which has good snow observations along with stream flow that we can look at and use. So both from just data analysis point of view and also from a modeling point of view. And then we're looking one on the East Coast in Vermont. So this is Sleepers River Basin. And so we have an interactive map for them to look at the different sites and the data that they will be analyzing so they can have a reference to what they will be doing with that data. So with that, I'll let Dave talk about the next part. This is stuff that he's covered.
Okay, so we basically figure that the students don't have a whole lot of information about snow hydrology. So we are, at the outset, we're giving them a lot of snow basics. And you can see from the learning objectives here that we've got, basic physical attributes of ice crystal formation, things like this, various snow processes. And for each of those, we've sourced an appropriate YouTube video. So there's a huge amount of information out there in YouTube videos that quite efficiently condense a lot of information into these video clips. So we figured that would be a good way for the students to go. So so we start off with some basics where we're talking about, snowflake formation, crystal structure, and we try to bring the thermodynamics in right from the beginning, and then move into some stuff about snowflakes and other meteorites that come to the surface. Next. So for that same set of videos, then we have a bunch of check your knowledge example questions. And so a lot of that is true false, just for them to get a good idea about what they learned and what they didn't learn in the previous segments. And so they can go back and check and see why it is that they were wrong. Right, so this is all just the check your knowledge on the snow crystal formation and thermodynamics. Next. So the next section is snow and meteorology, and we have another set of learning objectives, including processes governing lake effect snow, orographic lift, cyclonic flow, so that's like weather bombs. Understand how the Pacific Ocean and the eastern flow or western flow then gives rise to weather bombs, and also the El Nino and La Nina phenomena. So then we give them some opportunity to explore winter weather forecast tools from the National Weather Service. And the Weather Service actually has a lot of quite available information for people to self-educate on weather and hydrology. So we point them towards that. So then, we'll have these check your knowledge segments for them, just like in the first module. First slide. Next. Right, so here are the types of questions that we would pose for them for the snow and meteorology. First on lake effect, later on, lift from mountains, the moving into the weather bombs, stuff like that. The third section is snow measurement, and that's an important section for us. So we bear down on it pretty heavily. So this is where we start to have the students navigate into the web pages and stocks of information from the federal agencies. So first we send them to the National Water Climate Center webpage and find a bunch of useful data there or information there. And then they will, we get them to develop a technical vocabulary for snow. And we have some videos of snow pit analysis that they can watch and thereby understand snow even if they're not present where the snow is. And a lot of that is done in either Washington State or Idaho front. And we just sourced videos that were well done by primarily graduate students or federal agencies. Next. So as you see me flipping through these pretty quickly, then every time there's a colored set of content, like where there's the map, snow, courses, and aerial markers, usually that leads to a substantial amount of information related to that content tag. It's not really efficient for us to go through all of those today, but we have a couple of examples. So for example, on this page, you can see by 3.11, check your knowledge, then we show, okay, albedo, and give the definition for albedo, cooling degree days, what's the definition, dew point, etc., so that the students can relatively quickly get up the curve on the terminology. Next. Yep. Okay, so then what we haven't got into quite yet, because we've run out of time, is that there's a few different additional resources that will link these definitional segments to the more calculation part of the module. And so I think that it's probably time for me to go back to Josh on that.
All right. So the snow modeling section really is about helping the students learn to navigate a snow model, understand uncertainty in modeling, validation of modeling, and then understanding the individual model components that are part of that snow model. So the first part of this section really just looks at why are we doing modeling, what is the purpose, how can we use it, why do we want to use modeling. And then there's a broad discussion about model uncertainty and validation, and then putting in context within the snow model. There are a number of check your understanding activities. I'm showing one over here where they're looking at different validation measures of a model and being able to put them into different categories, of which we've talked about. So hopefully they have a good understanding of how they can evaluate the model that they're running, and it's not just a blind aspect of for running that. Then within the snow model components, we discuss in detail the different models that are there within the snow modeling. So there's 3 different snow models that we use. We use a basic temperature index model, which is just temperature driven based on an empirical melt factor. Then we have a hybrid model that uses some aspects of the radiation along with a melt factor. And then we have a full energy balance model that they can compare the differences. They can play with the parameters. And then we also have 2 different inputs that they can run for each of the sites. So one is using a gauge location that is near to the site, and the other is using the NLDAX forcing. And I have to clarify that for we're using the NLDAX forcing for a lot of the variables for both cases, but particularly for the gauge ones, we're looking at just using temperature and precipitation from the gauge, just to see what the difference is when you have different precipitation and temperature going into the snow modeling and the sensitivity that comes from that. So, so that's what this section is all about, giving them the background so they can actually run the model. And then we have interactive Jupyter Notebook for them to go and run on Google Colabs that will actually let them run the model and play with it live and test it out, so that they can actually interact with it and see how it works and look at some of the relationships of the model compared to the observations. So specifically, in the previous section, we're talking about measurements. We're going to have them do a similar collab where they can look at some interactions of observed processes, looking at the relationship between snow water equivalent and snow depth and peak stream flow relative to peak snow depth or SWE, and looking at those relationships in the model, and then again, or first in the observations, then again in the model, and comparing those, and also being able to select which model and parameters they think is best for each site. So that's the main learning activity within the snow modeling, and then the kind of capstone activity really throws in an aspect of the climate. So we'll talk a little bit about climate modeling, but then have the model, a different version of the model, or the same model setup, but with different climate forcings from CMIP 5 runs that they can then run the model over a limited period, to then be able to see how that may change in the future. And we've kind of put it within this authentic task. And the idea here is to have them produce a report about their findings and some background of the modeling and some limitations or uncertainties that may go with that. So I think that we have a couple of other information that we may use within the capstone aspect. But other than that, I think we're pretty much done and open to feedback and questions. So I did see that there was one question that popped up here on the chat that I can go ahead and address, but that's how easy it is for an undergrad student without Jupyter background to complete the activity. I think it will be. I've used Jupyter in my undergrad class before. If you write your notebook well enough, I can show you an example of it here. Let me exit out of this, but this is the notebook as is right now. But I really try to go through step by step, setting up the environment so it's really all coded so they can run it. It downloads the data. It sets up all the libraries that they need so they don't really have to worry too much about that. Imports the libraries after they set up the environment. And then basically it just has different things here where you can choose which site you want to run, which model, parameters. I'm going to clean that up a little more, make that a little more intuitive. But then I tried to have good discussion about how each of these things work and then walk them through that process. The idea behind this notebook is not to have them generate their own code, but more to have them just explore. So trying to make small changes in the code to see how things change, but not to necessarily write a whole bunch of new code. Any other comments or questions?
Thanks for explaining that, Josh. We have about 5 minutes left for questions.
So I guess when you've got these snowmelt models, what's the sort of spatial footprint or area that you think it's applying to? And I guess I'm getting towards what you think about the variability of snow within that area.
Yeah, so this snow model is certainly a simplification, and one of the things we talk about in it is it's just basically a lump model, right? So there is going to be substantial heterogeneity in the snow processes, and our models are not going to be well represented of that. But again, that's I think a limitation of how complex of a model do we want, and the purpose of this is to give them a basic understanding. And I think as long as we outline those uncertainties, hopefully that could be snow hydrology 201 or something, where we actually work more on some of the variability and spatial aspects of.
Do you outline those uncertainties?
What?
Do you outline those sort of that issue at least? Okay.
Right. So in the uncertainty section, I talk about how it's also there's temporal uncertainties because we're running this at a daily time step. So to try to make this run much quicker and make it more feasible for them to run on a reasonable time, it takes about 8 seconds to run 15 years worth of data. So I tried to make it quick. But then, we have temporal uncertainties because we're not really resolving the diurnal cycle of things. And then also the spatial aspects of it's lumped into one big snowpack or watershed. So.
Well, in the absence of any more questions, maybe we could show one of our videos.
Yeah, I don't know. Do we have time to share one of those? I don't know if there are any of them or that. How much time do we have left?
Some are short. The first one's short.
2 minutes left.
2 minutes? Is that enough time to show? Which one were you thinking, Dave?
First one.
This one here? Science of Snowflakes?
Yeah.
Right here. I don't know how well that'll work here. We'll see.
Distance has been. If you ever find yourself gazing at falling snow, why not catch a few snowflakes on your glove and examine their shapes? You might notice that they look symmetrical, and if you look closely, you'll see they have 6 sides. You could say a snowflake is simply frozen water, but compare one with an ice cube from the freezer, and you'll realize they're very different things. Unlike ice cubes, formed when liquid freezes into a solid, snowflakes form when water vapor turns straight into ice. But that still doesn't explain why snowflakes have 6 sides. To understand that, we need to delve deeper into the physics of water. Water is made out of 2 hydrogen atoms and 1 oxygen atom. A single water molecule thus has 10 protons and 10 electrons, 8 for oxygen and 1 from each hydrogen atom. The 2 electrons from oxygen's outer shell are shared with 2 electrons from both hydrogens as they bond together, and the remaining 4.
So we probably don't have time to watch it all. But yeah, in response to Iman's comment, we're working on getting all these videos and stuff that Dave's put together into HydroLearn. It's just not done yet. So it will be, just not there yet. So yeah, is there any other comments or suggestions? We're happy to hear anything else anyone may have.
Just on the Jupyter notebook, you may want to record like a minute video or something to show how students can interact with it.
Yeah, I put a video in there that shows an introduction to Colab, which has some interaction, but I may add one. I think it's a good idea to add one of myself just demonstrating the basics.
Yeah.
Especially on the first one.
Yeah.
Do you think you could include like a slider or a widget inside the notebook to allow them to play with any of the parameters or variables to see how it affects the model? Is that something?
It might be. I've not looked into that. That's a good idea. That's something to look at.
Yeah, they've got IPython widgets that has a slider, and so you can attach a slider to a parameter and allow them to adjust it.
To adjust it. That's not a bad idea. I like that idea. Appreciate it.
Mm-hmm.
All right.
All right, thanks, Josh and David.
Yep.
Remember to recommend this module to anyone you think might find it useful.